Okay, so before we at the recess week, we got ourselves introduced to the OS. All right, we talked about these state transitions. Okay, so what is new, what is ready, running, blocked, and exit. Right, so these are the main states. What we saw was, of course, by default, any new task that is created in the system automatically gets admitted into the ready state. All right, and there are multiple tasks that are always in the ready queue. All right, waiting for a chance to run. All right, and the scheduler, all right, a scheduler who is treated like the overall manager who will decide of all the tasks in the ready queue, one of them will be selected to transition to the run state. Okay, and then of course there'll be cases where you can get blocked, all right, where you maybe want something and you cannot get it or so on, and then you go to the block state. And if you eventually get unblocked, you will still transition back to ready. There's never a pathway from block to run. Okay, it's only block to ready, and then from the ready state, again the scheduler will come in and select. All right, and the selection, as we saw, was based on priority. All right, so the RTX RTOS is a preemptive priority-based scheduler. All right, which means that whichever tasks that are in the queue, the highest priority task will always get to run first. All right, that is how the RTX RTOS is designed. Okay, so we had gone through these questions, okay, and we went on to, we stopped at basically question 1, all right, where we reviewed the task transitions. Okay, so let's go on to question 2 on the RTX RTOS. Okay, so before that, let me share the link for the RTOS documentation. So I've done this before, but I will share it again in the chat. All right, so okay, so the link that I've sent in the chat, that is for the RTOS online documentation. Okay, it's always good to refer to the online documentation so that in case there are changes or updates, you get to see the latest one. All right, and it's quite well structured, so it's easy to search for what you want very quickly. Okay, so always keep this link with you, okay, on standby. So anytime you want to refer to any of the OS documentation, you can refer to it quickly. Okay, so let's come back to our discussion here. Okay, so here you are given a code. All right, so in this week's lab manual that I've already released, if you have tried it out, you would have already created your very first project with the RTOS already integrated in the entire architecture. All right, so I've given you all the steps, all right, how to include the RTOS libraries, okay, and compile and build your RTOS project. All right, so when you first start up, you'll get something like this, okay, where you have a main program, okay, and then you have a thread called app main. Okay, so we're going to understand how this works. Okay, so by understanding this question, you are actually also preparing yourself for the lab. All right, so you have an understanding or better understanding of what is actually going on when you do the lab for this week. All right, so the first thing is you can see that our starting point is always the main. All right, okay, so even though your system has an OS, okay, it's not only RTOS, any basic OS, okay, whether it's Windows or Linux or whatever, when you boot up, you don't just magically have an OS. All right, when you boot up, you still start with assembly language code first. All right, and then from there you can transition to you execute single-threaded code first, okay, and then eventually you have an OS loaded in the system, you can jump over to your multi-threaded environment. All right, so similarly over here, we are starting from main. All right, but it's important to note that when we say we start from main, actually in the back end there could be other assembly language code that runs prior to main. All right, but these are sort of hidden from us.
The slides aren't showing right now.
Not showing. Wait, sorry. Oh, okay. Sorry for that. Okay, sorry about that. Okay, so let me come back here. Okay, so in this uh, uh, sample code that you will actually see when you first create the project, all right, what you have is the this is what I mentioned. The starting point is still the main function. All right, that is very similar to your single threaded application. All right, only after you set up some important configurations for the system to run the OS, then you can switch over to the multi-threaded environment. All right, so it does not start off as multi-threaded. You start off still as a single-threaded, okay, without the OS, but you need to sort of initialize the OS and get it started up, and then you can transition over to the multi-threaded environment. Okay, so there are a few things here. All right, so first, let's look at this. Okay, this system call clock update, this is something we have been seeing all the while. This is just to make sure that the system is running at the frequency that we want. All right, so in some cases we run at the default frequency, sometimes we can run at a higher frequency. Okay, so that is a preference for us. Okay, the next thing is OS kernel initialize. Okay, this OS kernel initialize, what does it do? Okay, it initializes a lot of low-level sort of support blocks that the OS needs before it can start to run. All right, so before your OS can actually start to run, it needs to reserve some hardware blocks like maybe timers. You may need to reserve some sections of memory. All right, so it needs to do some setup first. All right, before it can actually start to load the OS and start running. All right, and all this is done by this OS kernel initialize function. All right, so this is provided to us by the OS library itself, so we don't need to worry about it. But when you call this function, basically what we need to know is we are actually setting up all the necessary back-end support systems so that the OS can run correctly on our platform. Okay, then after we initialize, then we can call OS thread new. Okay, so OS thread new, when we call, okay, there are three parameters that we pass in. Okay, so you can see first is app main, then is null, that is null. Okay, so null and null. Okay, so can you refer to your documentation and tell me what are these three parameters for? What is the first one, second one, and third one for? Okay, so your documentation is again back to your the link that I shared just now. All right, so if you go to that link, okay, you can search for OS thread new. Okay, so when you click on OS thread new, you will be able to see the details. Okay, so as you can see here, OS thread new, the three parameters are the actual thread function, the arguments, and then the attributes. Okay, so these are the three things. So the thread function is basically the name of the thread associated with this thread new that we are creating now. All right, so the name of the thread effectively. All right, when you create a new thread, you can also pass in some arguments. All right, so in this case, when we say null, that means there are no arguments to pass in. And the next one is attributes. Okay, so you will click on this OS thread attribute underscore T. We click on it, okay, it will bring you to another section where it can tell you some of these attributes. Okay, so under attributes, you have a lot of things here, such as the memory that you want to allocate, okay, for the stack, okay, for the control block, and so on. Okay, so generally we will not touch all of this, but one thing that we will try in next week's lab is this thing called the priority. Okay, so how do I create a thread with a different priority? Right now, when we say null, all right, we are saying is the default priority. All right, in next week's lab, you're actually going to explore this in more detail. So I don't want to go too much into it now. Okay, but next week's lab, we're going to explore this. So by default, it's called OS priority normal. So everybody has the same priority when you say null. All right, but of course, you can always create a new thread with a different priority. Okay, so I'll leave that for next week. Okay, but I just wanted to show you that first. Okay, so the three parameters, okay, the three parameters are the function name associated with the thread you're creating, the arguments, okay, okay, as well as the attributes. All right, so these are the three parameters that you call in, that you have to pass in whenever you create a new thread. Okay, so regardless how many threads you have, whenever you create a new thread, you have to follow this process to create a new thread in your system. Okay, so now the next important thing. Over here, you call OS thread new and you create this new thread called app main, correct? So this app main, as you can see, is over here. All right. Now, when will app main be called? Okay. So will it be called the moment I create the thread? Okay. Or when will it be called? Okay, so Neil says line 26. Okay, when I call OS kernel start. All right. Any other ideas? Any other thoughts about this? Okay, so when we come to line 26, okay, which is OS kernel start, okay, so this is the point, all right, where we are transitioning from the single threaded environment to the multi-threaded environment. All right, before this line, okay, before line 26, okay, before line 26, okay, up to here, you are still operating in the single threaded mode. Okay, from line 26 onwards is where you go to the multi-threaded mode. Okay, so when you switch over to the multi-threaded environment, that means the OS has kicked in. All right, when that happens, okay, all your threads are now at the sort of mercy of the scheduler. Okay, they are the mercy of the scheduler. That means the scheduler, based on its rules and the state of the task, will decide who gets to run. Okay, so there is no guarantee as to when admin will be run. But of course, in this case, since there is no other task in the system, right, there's only one task created, which is admin, we can say that after the OS is started, admin will run. Correct? But it will not run just because OS has started. It's after the OS has started, the scheduler has to kick in. The scheduler has to look at all the tasks in the ready queue, and then it will make a decision of who to run. Okay, so at any point of time, there can be many tasks, okay, that are in the ready set. All right, and the scheduler will choose the highest priority task to run. All right, of course, in this example, you only have one task, correct? And so you have no other tasks that can be higher priority. So in this case, your admin will run after OS has started. Okay, but in reality, you have many tasks. All right, so the highest priority task will run first. Okay, now let's look at the next question here. Inside the admin, okay, you see this for loop. Okay, this is basically an infinite loop, all right, while one loop. All right. So why do we want a while one loop? Okay, the main. Okay, so the answers here. So most of the answers are quite similar. You want to. Okay, so it's either. Okay, so when you say while one, all right, most of you get the idea that you do not want it to end, correct? So when we do not want it to end effectively, it means that we always want the task to be alive. All right. So you can see there is two things here. All right. One is infinite loop here in the main, and the other infinite loop here. All right. Now this loop here is basically by right you will only come back to this infinite loop if your OS crashes. Okay, because when I start the OS kernel, I switch over to the multi-threaded environment. So if something goes wrong and your OS suddenly stops working or it crashes or something, coming back to the single-threaded environment, you may still be stuck in this while one loop. So your system seems to be alive, but actually the OS has already crashed. All right, so that is this for loop purpose. All right, but what we are interested in is this particular for loop over here. All right, and the reason why we have a for loop in the task. Okay, so this main is the task that we are running. Correct. That means this is in the context of the multi-threaded environment. All right, and in the multi-threaded environment, if you remember the last lesson we had, we said that the tasks are designed to run forever. Okay, why we do it that way is because it is not the case where you have a general purpose OS system where I double click on your Microsoft Word and it opens and then you just close it, all right, and then you can just click on it again or something like that. No, all right, in an embedded environment, when you start up the system, all the tasks will be sort of started up, all right, and of course not everything will run, all right, some may be block state, some may be ready state, okay, but effectively everything is written in a loop because as and when you need this task to do something, you will be able to wake it up, all right, and ask it to do some action for you, all right. And in order for the task to be alive in the system, it always has to be in a while-one loop. Okay, if you do not have this while-one loop, okay, what will happen is your task will just run one time, and after that, it will abruptly terminate. Okay, you will never be able to run again. Okay, so the while-one loop is there to keep your task always in a state where it can always be reactivated, all right, whenever you need it to run. Okay, so all your code, okay, all your code actually is inside this while-one loop or for infinity for loop here. All right, so you will see in the example that we are looking at, you will see how this actually works. All right, so of course the question then is, if I'm stuck in a while-one loop, how will other tasks run? How will I get to switch over? So there has to be a mechanism in place to allow other tasks to also run. Okay, so every task will be written like this. Every task will be written in a while-one loop. Okay, so the whole idea is the task behaves as if it is running forever. Okay, that it has the CPU to itself. Okay, but we as the developers have to put in some safeguards, some framework to allow multitasking to happen. All right, so that is what we're going to be learning. All right, so that's what I mentioned just now. In embedded OS system, generally tasks are written as forever loops. Okay, if you only want to do something once and you don't want to do it ever again, then there's no point creating a task. You just call a function. All right, and you call that function one time and that's it. All right, so only if you know that this activity is going to keep occurring, okay, a few times, all right, during the lifetime of this product being on or in the on state, then you have to write it in a task to manage this multitasking. Okay, now let's look at this code over here. Okay, so in this code we have this app main and main. So this is the single threaded code here, okay, where we run. So this is the things we have already done before. All right, and over here I create a new task over here, OS thread new app main. All right, and once I create, I call OS kernel start. So inside here, once I call OS kernel start, I switch to the multi-threaded environment, and in the multi-threaded environment, I will come here, correct? Okay, when will I come here? Like what I mentioned just now, the scheduler will see. Okay, so I got no other tasks in the system. I only have app main in the system, so app main will be selected to run. All right, so when I come on the scheduler selects app main to transition to the run state, so I'll come in. All right, and then this while-one loop over here, what do I do? Okay, first I on the LED, then I call OS delay for 1000, then I off the LED, then I call OS delay again for 1000, and this thing goes on indefinitely in a while-one loop. All right, so that is basically what is happening. So basically once I transition to the multi-threaded environment, I will never come back to main. It is all only between the tasks that I created. Okay. Now, so let's look at the first question here. When we call OS delay, what happens to the app main task? So when I call OS delay, what happens? All right, so if you're not sure, go back to the documentation and search for OS delay and see what exactly does OS delay do. Okay, so good. So I see the answers coming in. Okay, so let's refer back to our documentation here. Okay, so if you look back to our OS delay documentation, it basically says that this function waits for a time period specified in kernel ticks. All right, and the delay thread is put into the block state. All right, and the thread is automatically put back to the ready state after the given amount of ticks, and if this is the highest priority, then it will be scheduled immediately. Okay, so as you can see, the documentation is quite clear. Okay, so basically when I call OS delay, I will put myself into a block state. All right, so this you need to okay, so important thing to note is some of these implementation details may vary from OS to OS. Okay, so the concepts are still the same. All right, multi-threading, mutex, semaphore, message passing, all these things you're going to study, the idea is always the same, but some of the minor details of whether it goes to a block state or whether it goes to a ready state, okay, some of these things can be a bit different for different OS. Okay, so why I say this is because I deal with other OS before where OS delay will make the task go to a ready state, okay, and not to a block state. Okay, so it's good to read out the documentation to know specifically the OS you're working on, how it behaves. All right, because that understanding can impact your code a lot. All right, so you need to know exactly what state my task will transition to when I call this particular OS function here. All right, so we talked about the ticks here, it was mentioned. So what is a tick? All right, so the default system configuration is one tick is 1 millisecond. All right, so 1,000 ticks is 1,000 milliseconds. All right, so this gives us a very nice way of having pre set delays in our code, all right, without having to calculate anything specific. Okay, so okay, if lower priority task is running and a higher priority task is in ready state, the lower priority task gets completed first. Okay, so the moment a higher priority task comes into the ready state, your scheduler will automatically switch to the higher priority task. Okay, so that is the nature of what we call a preemptive priority based kernel, okay, which is how the RTX is defined. Equal priority, okay, good question. We will look at that in a while. All right. Can we refer to this site during the midterm? Good question. Let me think about that. Okay, so let's look at the other concepts first, all right, and then we will also come to that equal priority thing later. Okay, now when I call OS delay, okay, we just saw that OS delay puts my task into a block state. All right, okay, so if I look at admin, okay, if I look at admin here, okay, so initially I'm in the ready state, okay, and then I transition to the run state, okay, because there's no other task. All right, and then I call the on function for the LED. All right, and then when I call the OS delay, what happens? I transition to the block state. Okay, I transition to the block state. Now, when I transition to the block state, what will the CPU execute? Because I know that I'm going to be blocked for a total of 1 second. All right, and there is no other task in the system, right? You've only created one task. Okay, you only created one task. There's no other task in the system. So what will I execute during this 1 second? Okay, so there's a few different ideas. Okay, some say it's the for loop in the main function, some say nothing. All right, so basically, all right, this for loop in the main function here, okay, we should never come back here. All right, because the moment I execute OS kernel start, okay, I transition to the multi-threaded environment. All right, the main is part of the single-threaded environment. All right, once I call OS kernel start, I should never come back to main. I should always only be transitioning within the multitasking environment. I should never come back to main. All right, so in a situation like this, where I've only created one task, all right, and there is nothing else created, and this one task that I created also go to a block state. So what is happening? All right, so the OS itself has background tasks that it will create. Okay, so these are things that will happen during the initialize function. All right, so when it's initializing, it will actually also create other background tasks to help it manage all the different things that are happening. Okay, so there are things like timer tasks, okay, and there's also another task called idle tasks. Okay, later I will show you. So these are background tasks that the OS actually creates and will be running even if all your application specific tasks are in the block state. Okay, so this is what you will see later. Okay, so he has his own idle thread as well as timer thread, okay, that it will actually run in the background. All right, so these are sort of, again, hidden from the developer because you don't have to mess with them. All right, those are controlled by the OS and managed by the OS. All right, so if all your tasks are in the block state, okay, whatever is the case, these tasks will still be running in the background to keep on checking on what is happening, what are the activities, all right, when to switch and so on. Okay, can we still create threads after OS kernel start during runtime? Yes. Okay, so OS, to create a new task, you call OS thread new, and this OS thread new can be called anywhere in the OS environment. All right, so even after I call OS kernel start, I can still create new threads after that. Okay, it doesn't have to be before the OS kernel start. All right, but you always have to create at least one task before the OS kernel start, so that the moment the OS kernel start is called, you transition to that first particular task, okay, as a starting point. And then from there, you can create. Okay, so that means inside this admin, I can also call OS thread new. Okay, and create another task here, also can. All right, or I can call all the OS thread new first and then OS kernel start. Okay, so there are different ways of doing it. Okay. Okay, now let's go on to the next question here. If we use a normal delay routine, okay, like what we have been doing so far, will we see the same effect? All right, so what I'm saying is, instead of saying OS delay over here, okay, instead of saying OS delay, I replace it with my normal delay, okay, the one that you've been using so far. Okay, I put in some value. Okay, a normal delay. Will we still see the same effect of LED blinking? Okay, so a lot of interesting answers. Some will say yes, some say no. Okay, same effect. Okay, but other tasks may not be able to run. Okay, good. Okay, so let's look at this first. Okay, so can you see the screen, the code? Okay, good. Thank you. All right. So okay. So basically, this is the code. Okay. So so in this we have the OS LED red thread. All right. And over here you have this same thing. So let me just demo to you the original one, which is the OS delay. Okay. So you see, where is my camera? Okay. So here is the code, and here is the my board at the side here. Okay. So let's run this. Okay, so as you can see, the LED is blinking red, okay, on the screen here. All right, so now what I'm going to do is I'm going to put a breakpoint at the OS delay over here. Okay, and over here you can see, I'm not sure if I can zoom in here. Okay, but over here you can see on the call stack, this is the OS RTX timer thread and OS RTX idle thread. Okay. I don't think I can zoom in here. Okay, but later on in the lab, you can see. So on the bottom right hand corner over here, you can see in the call stack, I have OS RTX timer thread and OS RTX idle thread. Okay, so these are the background threads that I mentioned earlier. So this will run, okay, regardless of anything else that is running in the system. All right, so here you have your LED red thread that is running. At the same time, you have your timer thread, idle thread. So these are created, okay, when you call the OS kernel initialized, okay, by the OS itself. All right, so coming back here, you can see that if I remove the breakpoint and I resume, okay, we will carry on with the blinking of the LED. Okay, so now let me stop. Okay, and what I'm going to do is I'm going to put this delay function here. Okay, so what I'm doing is I'm replacing this OS delay with this delay. This delay is basically the one that I given to you last time. All right, where you can use it to just create some random delay. Okay, if you want to see some LED blinking. Okay, so now if I were to run this, okay, so you can see the LED is still blinking. Okay, of course it's blinking a bit faster because this is number that I put in is not exactly related to 1 second, but effectively the effect is still the same. All right, but I think most of you have already pointed out the main difference, okay, in the chat just now. The main difference, okay, between this, okay, and the OS delay is that the OS delay, okay, frees up the CPU. Okay, the OS delay frees up the CPU. All right, which means that you are okay, the OS delay frees up CPU, so you are able to do other things. All right, if I put delay with my normal routine, okay, you are still holding on to the CPU. All right, so effectively you're hogging the CPU, all right, and you are depriving other tasks of using the CPU. Whereas if I use OS delay, I put myself in the block state. So if you remember the transition, when the task that is running, okay, if I have a task that is running and I transition to the block state, Okay, that means whoever is in the ready, okay, the scheduler can select somebody else to come in and run and use the CPU. So that is basically one of the mechanisms in place to help us transition between the different tasks. So that is why even though I write every task as an infinite loop, it doesn't mean that the task is going to hog the CPU forever. All right, so you must put in mechanism in place like this to allow a task to transition out whenever it can, so that some other task can use the CPU. Okay, now let's come to this. Okay, something interesting here. So here I have two threads, LED red thread and LED green thread. Okay, both of them written in exactly the same way. Same delay, everything. All right, and the green LED, only thing is red LED and green LED. Okay, so let me transition back to my code over here in the camera. Okay, so let me show you the code first. So, okay, so now I'm going to uncomment this one and I'm going to switch back to my normal OS delay here. Okay, so the LED red thread, okay, and the LED green thread are exactly the same. Only thing, one is red LED, one is green LED. And inside my main, I have created two threads. Okay, LED red thread followed by LED green thread. Okay, and I call OS kernel start. Now, when I run this code, okay, when I run this code now, what do you think will happen? Okay, so I have actually a poll over here. Okay, so I'm going to launch the poll now. Okay, and tell me what do you think will happen with this code over here. Both of them exactly the same. Okay, same code, LED red thread, LED green thread, exactly the same. All right, and then I start the program now. What do you think will happen? Okay, the LED code is the same as what you have in your tutorial. Okay, both of them is exactly the same. LED on, OS delay, LED off, OS delay. Same thing for LED green, LED on, OS delay, LED off, OS delay. All right, in the main function, I have called OS thread new for LED red thread, followed by OS thread new for LED green thread. Okay, and then I call the OS kernel start. That means I transition over to the multi-threaded environment. Okay, so I'll give you all a few more, about 10 more seconds to make a decision. Okay, so let me end the polling and share the results. Okay, so majority of you have chosen the option where both LEDs on and both LEDs off, but a good proportion of you have other ideas as well. So about 35% of you have other ideas where either red LED on and then green, and some say only red. All right, so let me close the poll, okay, and let me come here. Okay, so let me run the code. Let me do the code and run it. So that'll be the moment of truth, correct? Then you know what's happening. Okay, so let me run it. Okay, so what do you see? It is actually yellow color. Okay, so maybe not so clear on the camera or on your side. Okay, but it's actually yellow color blinking. Okay, so you don't see red, you don't see green, but you just see yellow only. All right, so why do we see yellow blinking? Okay, so of course yellow means red and green together is yellow. All right, so majority you got the answer right. That means both of them are sort of switching on at the same time. All right, and switching off at the same time. All right, but is it exactly the same time, or what is actually happening? All right, so let's uh, look at this. Okay, so in this case, what would be expected behavior? Okay, so let me draw it out here so that you understand what is happening. Okay. Okay. Okay, so now I have created two threads, LED red, okay, and LED green, two threads over here. Now, so we know that the moment you create OS thread new, both of them are in the ready state. Okay, so both of them are in the ready state. Now the important question, when I call OS kernel start, who will run first? Both of them are the same priority, correct? Okay, both of them are the same priority, but who will run first? The scheduler has to select somebody to run first, correct? So who will the scheduler select to run first? Will it be LED red or will it be LED green? Okay, so let me come back to my code over here. Okay, so the answer to that question actually lies in the code. All right, because it all depends on the sequence of who was created first. All right, because whoever was created first would have been the first one to be in the ready queue. All right, so even though they are the same priority, LED red thread was created first. So LED red thread was in the first one in the queue, followed by LED green thread. So in terms of the same priority level, they are in the queue, but LED red was created first. So that is the first in the queue, followed by LED green. All right, so the answer is actually here. All right, because I created LED red thread first, LED red will run first. All right, because they are both priority. So priority wise, it won't make a decision, but it will be because LED red thread was created first. The default priority is what we call OS normal priority. All right, and then from there you can increase or decrease. All right, so the normal priority is just kind of the exact number right now, okay, but you can actually increase or decrease that number in the code, okay, when you create a new task. Okay, how do you adjust priority? That one is next week's lab. Okay, so we will do it step by step. Okay, so next week's lab we're actually going to do this. We're going to be changing priority, and then you'll see the effect. All right, and just now, if you remember, I said that is one of the attributes. Okay, the first one is the app name, the other one is the argument, the third one is the attributes. All right, so under the attributes, one of it is priority, and we will be doing that for next week's lab, how to change the priority of a task. Okay, so coming back to this here, so when LED red thread, since the first one in the queue, it will transition to the run. Okay, so this one will stay in the ready state, all right, and it will run, and when it run, what happens? It will switch on the LED, on the red LED, and then it will go to call delay, correct? So when you call delay, what happens? It will go to a block state. Okay, so it will block for 1 second. All right. Now, so of course, when it goes to a block state, the next task in the queue will actually transition, or will allow a transition over. That means since the LED red thread goes to the block state, the scheduler. So at this point of time, the scheduler will come in, okay, and he will see that, okay, now I have LED green thread in the queue, in the ready queue. So I will transition LED green thread over to the run state. All right. So technically, even though we see yellow blinking, we actually have only red first, followed by green, okay, and then you see them as yellow together. Okay. Similarly, when I off, what will happen? The red LED thread. Okay, so this red LED thread will come out of the delay first. So I will off the red LED first, and then I will transition, and the LED green will come out of the delay, and then I will off the green. So there will be a short period of time where you will see red on first, and then green on later on when you're going to off. Okay, so let me show you that. So of course that one you can't see it unless you have some superhuman powers, you can see it. All right, normally, all right, but normally you can't see it unless you do a breakpoint, okay, because it's too fast. Okay, so let me show you. Okay, so this is basically the code. Just now the red, yellow LED blinking. Okay, so what I'm going to do is I'm going to put a breakpoint here. Okay, so now what is happening? So I put a breakpoint here. That means at this point of time, both the LEDs are off. All right, and right now what is going to happen is I'm going to on the LED. So let me put another breakpoint here and run. So this is the instance where the red LED is on first. Okay, and now what I'm going to do is I'm going to put another breakpoint here. Okay, so what is going to happen now is when I run the code, this LED red thread will transition to the block state. Okay, which will allow the LED green thread to run and switch on the green. So right now you see it's a red. Okay, but once I transition over to the green LED thread and the green LED is on, okay, you will see that it transition to the yellow. Okay, so now you see it become yellow. Okay, because right now both the red and green are both on together. Okay, so let me put a breakpoint here and put a breakpoint here. Okay, so I'm going to run again. Okay, so now what has happened? I have completed the 1 second of on for both LED red and LED green. All right, so both the 1 second has transpired, and so now, of course, the 1 second of the LED red thread finishes first, correct? Because I called it first. So right now I come back to the LED red thread. So I transition from the block state to the ready and now to the run. All right, and now what I'm going to do is I need to off the LED. So right now when I off this LED, you will see that this is the point where I will off the red. So the green is there. Okay, because the green is still on. All right, and now if I come here and okay, if I run, okay, now I come to the LED green thread. All right, and now if I put another breakpoint and I run, the LED green goes off. Okay, so there is a brief moment of time where LED red will be on, okay, and then both will be on together. Then another brief moment of time where the LED red will be off and only green will be on. Okay, so over that you can't see unless you put the breakpoint. So that is why you only see it as flashing yellow, red and green together, on and off. Okay, how long does it take to run each line of code? All right, so that one, it depends. So it is not one clock cycle, correct? Because if you look at it from the processor perspective, your code will be translated to assembly and so on. So each code can take many clock cycles to run. Okay, so it is not one line, one particular clock cycle. So you have to look at it from the assembly language if you want to know how many clock cycles are being used, okay, for instruction. Okay, so this timeline is basically what I just showed you just now. Okay, but you can when I share the result, I mean the solution, you can have a look at it again. All right, so this gives you the idea of what I mentioned just now. All right, but we will come back to this in a while after we look at the next question. Okay, oh sorry, I never include the next question. Okay, so let me ask the next question. All right, the next question that we need to look at is this. All right, now let's say I have the same code. Okay, so I think that I did not include the tutorial, but it's something that we need to discuss so that you know exactly something important. Now, this same exact same code, right now what I want is I want to change this OS delay and put my normal delay, the one that we did earlier. Okay, that means the red LED thread, okay, instead of OS delay, I want to put normal delay. The green one is still having normal OS delay, but the red one, I want to do this delay. All right, so let me rerun the poll, and can you all tell me what do you think will happen? Okay, so only for the LED red thread, I'm going to change this now. I'm going to change the OS delay to this delay routine which we have been using all the while. Okay, so okay, so let me end the poll. I think 96% of you have voted. Okay, so if you look at the results, majority of you have selected the option which is only red LED blinking. All right, and I think the decision of this being the choice is because, as we discussed earlier, this delay is still consuming CPU resources, correct? So you do not transition out of the running state, whereas OS delay allows you to go to the block state, which means another task can run. All right, so let's see what happens. Okay, so let me run the code. Okay, so let me come back here. Okay. Okay, so this is still the old code, right? So everything else the same except that my LED red thread is going to be replaced with this. All right, so everything else remains the same. LED red thread only replace the OS delay with this delay, and LED green thread is the same. And in the main function, we call OS LED red thread first, followed by LED green thread. Okay, so let me build the code. Okay, so let's see, this is the moment of truth, correct? Okay, so if I run, we expect it to be red LED. So let's run. Okay, and what do you see? You see that there is some green, okay, there is some red, and there is some yellow. Okay, why is it like that? Okay, if you see green and if you see yellow, that means technically the LED green thread is also running. Right, the LED green thread is also running. That is why you can see some green, you can see some yellow. Okay, so why is it the case? Even though I have used this delay function, which is not a OS call, that means I'm still hogging the CPU. All right. So it sort of contradicts what we just discussed, correct? Because we just discussed that this is hogging the CPU, so I cannot go into a block state. All right. So I'm still running the CPU. All right. But then if I'm seeing green, I'm seeing yellow, that means I'm actually having a context switch happening. Correct. That means I'm actually going to LED green thread, and there are also cases where both are running together. All right. So why is that the case? All right. So this brings us to another thing. All right. Which is actually something you're going to be exploring in the lab. All right. In the lab, okay, what you're going to be seeing is if I have tasks, okay, if I have tasks that are of the same priority level, all right, which in this case LED red and LED green, okay, there is actually another level of scheduling happening, which is a round robin scheduling. All right, so the way the RTOS RTX works is when I have threads which are in the same priority level, and if they are all in the ready state, then you will actually do a round robin among them. Okay, again, this is something that is a bit unique to RTOS RTX because some other OS don't have this policy. Okay, some other OS, what they will do is, regardless of same priority, if one task is running, it will still run until it sort of goes to a block state or gives up the CPU. All right, but RTX does it a bit differently. All right, it actually does a round robin, and that is actually inside this file called rtxconfig.h, where you this is enabled by default OS round robin. Okay, so again, this is something you will be exploring in the lab. Okay, so every 5 ticks, so this is the OS robin timeout. So every 5 ticks is where you will actually do a context switch. Right, so this is something again very unique and sort of seen in RTX RTOS, which again you may not see in other OS. All right, but this explains why we have this behavior where I hog the CPU, sort of hog the CPU here, but I still have context switch happening because they are both of the same priority. All right, so again, don't be too concerned. In the lab exercise, you will actually be going through this. Okay, I'll be going through this. Okay, so I took almost 1 hour to complete the tutorial, but I think it's important, all right, so that everybody has a good understanding of what is happening. And when you do the lab, you actually appreciate what you see. All right, so just don't do it just going through the motion, but you actually understand what is happening at the back end, okay, especially how the OS is operating. All right, so let's go for a break now. All right, now it's about 10 o'clock, 10:02. We'll come back at 10:10. All right, and then we will start on the lecture 11, okay, on scheduling. All right, so don't worry about if anything is still not sure. In this week's Friday's lab, okay, we are going to go through this, okay, in the lab manual. All right, of course, you can also do it at your home right now since everything is with you. All right, and then you actually see this in action. All right, and any doubts you have, you can also ask me, okay, on Friday in the lab also. Okay, so let's go for a 10 minutes break, and I'll see you back here in a while. Okay, so welcome back. Let's carry on with the next topic on scheduling. Okay, Okay, so before we start on the topic, a few things I just wanted to highlight. All right, so I think we had your mid semester feedback session with the students. All right, so this was of course across all the modules. All right, and I think for our module, one of the feedback was about the lab demo, being delayed, because of the huge number of students, especially for the group one lab session. All right, so of course I discussed this with the TAs, and I think it's a good problem. All right, the reason is because each group had a lot of questions and a lot of things to clarify, so the TAs took more than expected time with each group, right, doing the demo to clarify their doubts and clear their questions. All right, but of course I know this cannot carry on, because if not, everything has a huge backlog towards the end of the semester. Right, so that's why moving forward I sent the announcement that for the remaining labs, so starting from week 6 lab onwards, all right, there will no longer be a requirement for any demo. So there's no report as well. Okay, so if in the lab manual you see some word of a report or something, just ignore it. All right, there is no report, there is no demo. All right, but of course I have put in questions, all right, important questions that you need to review yourself, with your friends or whatever, just to make sure you understand. Okay, so if those review questions in the lab manual you are unable to answer, okay, you're not sure, then you need to approach me or approach the TAs, all right, during the lab session, and clarify what is it you do not understand. Okay, so those questions are meant to make sure that you don't just copy paste the code, or and just see it working and you're happy. All right, we want to make sure that you actually understand what is happening. All right, so that is why those review questions are there. Okay, so that is why moving forward we will no longer have any requirement for demo. All right, of course, like I said, please don't take it that okay, no demo means I can just relax and don't need to worry about anything. But like I said, it's important for you to go through the questions and the labs so that you really know what is happening. All right, and like what I mentioned in the beginning, all the labs are actually designed to work and build towards the final project. All right, so by doing the labs correctly, by working on the hardware, the code, everything, you are actually moving towards the final project. All right, very progressively, week by week. Okay, so another two things again, students have been asking is the project budget and hardware component replacement. Project budget, as I mentioned before, is $40 per team. All right, so you can buy anything that is related towards the project. You do not need to buy anything to complete the project. Okay, let me repeat that. You do not need to buy anything to complete the project. I have already given you everything you need to build, assemble a completely working prototype. All right, this is only if you want to enhance something. All right, and I think most of you have been talking about buying a new speaker because the buzzer is so beautiful, so fantastic. All right, so you want to replace it with another speaker. Okay, that is fine. All right, you can buy any speaker you like. Okay, just remember that whatever you buy, you must keep the receipt. All right, claims are only processed at the end of the semester. All right, at the end of the semester, I will send you all the documents to fill out and put the contact, and then the claims will be processed after that. All right, I will also send you all the links to the Freedom board. Okay, so that is of course another common thing that sort of fails. All right, so that is another thing you can buy. All right, besides that, the other components like motor drivers, Bluetooth module, these are also things that occasionally fail. All right, so if yours fails, you can ask me or ask the TAs first to see whether we have a spare. We will do a replacement for you. All right, if you run out of replacement, then you must buy. All right, so that is for the project related matters. All right. Okay, so let's go on to the schedule here. So this is basically what we've been looking at, okay, in the last lesson as well as in today's early on tutorial review. Okay, so here basically what we have seen is we have multiple states that a task can be in. All right, and we need to, or the person who's in charge is basically the scheduler. Okay, and what we have understood so far from the RTX perspective is it is a preemptive scheduler. Okay, so when you say something is preemptive means when one task is running, it can abruptly be sort of pushed aside to allow another task to take over based on some decision making by the scheduler. And a preemptive scheduler makes decisions generally based on priority. All right. So that is how the almost all RTOS behave. Okay. When you say RTOS, okay, the whole term RTOS means real time, and this real time comes with the concept of priority. That means somebody or some task that is more important should be given the priority to run its code. Okay, take over the CPU. Okay, so that is basically how the RTS RTOS works, similar to many other real-time operating systems. All right, so in today's lecture, we are going to have a closer look at a scheduler in a general sense and what are different type of scheduling policy that are actually implemented by different type of OS-based systems. Okay, so a scheduling algorithm, as we have seen, is basically a set of rules. Correct? How do I decide which task to allocate to the process? So when I have task A, task B, and so on, task T, so all of them are in the ready queue. Okay, so how do I decide which task gets to be allocated to the processor? But of course, the scheduling algorithm must also be such that you want to make sure that all the tasks meet their deadlines. All right. So of course, when we say a deadline is basically a time by which you want some activity to be completed. All right. So let's look at it. All right, from a sort of theoretical view. All right. So in our analysis, if you look at this slide, this whole slide has some sort of presumptions which may not hold true in many cases. All right. So the thing that we look at is in this set of slides, one of the things we assume is that most tasks are periodic in nature. All right. Many algorithms, okay, to make the analysis sort of hold true, you need to make some assumptions. So one of the assumptions that most scheduling algorithms make is that the tasks are periodic. All right, so when I have multiple tasks and all of them have some periodic interval at which they run, then how do I schedule them such that everything can meet the deadline? Okay, now let's look at these three tasks here. So in these three tasks, A, B, and C, I have different execution time and different deadline. All right, so execution time is basically the time that you take to execute your code. Okay, execute your code. This deadline is basically by how much time I must complete my execution of that particular task. All right. And the worst case scenario is always what? The worst case scenario is when all tasks are ready at the same time. All right. So at time t equals to 0, all the tasks, task A, task B, task C, all three are ready. That means all three are ready. That means they can use the CPU. So who will the scheduler select to use the CPU? Okay, so let's take this scheduling algorithm A, B, and C. So if I run A takes 10 milliseconds. So each block here represents 10 milliseconds. Okay, each block here is 10 milliseconds. Okay, so A will run for 1 block, B for 2 blocks, and C for 3 blocks. Okay. Now let's look at the deadlines. The deadline for B is 20 milliseconds. All right. If I look at this, what do you see? You see that the B misses its deadline. All right. The deadline is calculated from the time the task is ready. Okay, from the time the task is ready. So from the time the task is ready, I should complete this particular task before the deadline. And if all the tasks are ready together at time t equals to 0, and if I schedule it in this order A, B, and C, you find that B will miss the deadline. For A, no problem, C, no problem, but B misses the deadline. Correct? Now, how about if I move things around? All right, I say B, A, and then C. So B runs first, followed by A, followed by C. Okay, so looking at the deadlines, you can see that I can fulfill a deadline for B, fulfill the deadline for A, and fulfill the deadline for C. So all the tasks will meet the deadline. All right. So the same set of tasks execution time, deadline the same, but just reordering between who goes first, who goes second, decides whether the task can meet, all the tasks can meet the deadline or not. All right, how about I change
Is the
it?
task
Sorry?
finish by the deadline or start by the deadline?
Sorry again?
The deadline, is it finished by the deadline or start by the deadline?
Finish by the deadline. Okay, so I need to finish that particular activity by the time the deadline is up.
Okay, thanks.
Okay, so now I swap things again. I put B, C, and A. All right. So again, let's look at the deadlines. So B, no problem. A, I miss. All right. C, no problem. So you can see that if I schedule B, C, and A comes at the end. Okay, but A's deadline was 50 milliseconds. All right. So it is quite important, right, that we make sure that we schedule them in a way that the deadlines can be met. All right. So this simple example. So here we are of course not following any theory. We're just randomly trying different options. All right. And one of them is correct, and one of them allows us to meet all the deadlines. All right. But of course, there is a better way to do it, which we will explore later. Okay. So let's look at some terminologies. All right, that we will be using. Okay. So like what I said just now, we are going to have some assumptions that we're going to hold throughout this analysis. That firstly, we have a fixed number of tasks. Right? So in the system, there is a fixed number of tasks, and the tasks are periodic. All right. So of course, this doesn't necessarily hold true, like even for our own project. All right, because we don't say that you will send a Bluetooth command every 5 seconds. No, correct. Sometimes you send, sometimes you don't send. Okay, sometimes you run the motor, sometimes you don't run the motor. So in reality, of course, some of these assumptions do not hold true. All right, but for analysis sake, we make some of these assumptions and then we try to see how well we can schedule them based on these assumptions. Right. So again, some of the things is periods do not change with time. A task can be seen as an infinite sequence of instances. All right, and once a task instance is released, all right, it becomes ready at the beginning of each period. Right. So what you're saying is, if I have a task, all right, that is, so if you look at this task 1, for example, these are 3 instances of the same task. Okay, the period is the same. So maybe, for example, I release this task every 5 milliseconds. That means every 5 milliseconds, that instance of task will be sort of released, and within each instance of that task, all right, I will be ready the moment I release it. All right. So it's not that I release it and then suddenly I become blocked. No. Okay. So the moment I release the task, I will be ready. And at the same time, you can see that each instance of task has different computation time. Okay. So task 1 is a bit in the middle. Task 1 is a bit shorter. Okay. So instance 3 is a bit longer. So each instance has different computation time. All right. So that is basically the next thing which we're going to look at, which is called the worst case execution time. Right? And this is quite common, right? Because when you write a piece of code, right, you may have loops, you may have if else, and so on. So depending on those input conditions at the time, in some cases you may run the loop for 1,000 times. In another instance, you may run the loop only 10 times. All right. So it depends on what were the conditions each time you ran that task. All right. So we need to look at the worst case execution time. So what is the ultimate upper limit of the execution time for that particular instance of a task? All right. So again, like for example, a sorting. All right. So different set of inputs may give you different results because the data is different. So we need to look at what is the worst case execution time. Okay, and that is the C. Okay, what the term we use is C. And at the same time, we have another parameter called the deadline. So the deadline is basically, we can say that in our case, we assume deadline is the period. Right? Why? Because the period is the interval in which I will release the next instance of the task. All right. So if I do not complete the current instance by this current period, then something is wrong. I cannot release the next instance. All right. So I need to make sure I finish whatever I need to finish within this current instance before the next instance is released. So we assume that the deadline is equals to the period, and definitely C must be less than or equal to D, correct? Computation time, means the worst case execution time of the task must also be lesser than the deadline, correct? I cannot have a task that may take 5 milliseconds to execute, but yet I want to repeat that task every 3 milliseconds. It's not going to work. Okay, so you need to make sure that the deadline is shorter. The worst case execution time is smaller than the period, which is also the deadline. All right. So again, these are some additional assumptions. Tasks are completely independent of each other. All right. So again, this is definitely not true for us as well, because in our case, many tasks have a lot of dependency on each other. All right. Your Bluetooth, your serial monitor task has some dependency on how it will influence the motor control task, how it will influence the audio task, and so on. Correct. So your sensor task may interfere with the motor control task. So everything there is some dependency. All right. So again, these are things that we just for now we take it as independent. All right, just for the analysis part. All right. And system overhead for scheduling and context switch are negligible. Right, as what we saw before, you have a task A that is currently running, okay, and I want to switch to task B. Okay, so if task B is currently blocked, okay, and I want to switch to task B at this point of time, there is a context switch. So a context switch is basically your saving and restoring of your processor state. Right, so task A must save its context, task B must restore its context, and then task A can go to a block state, right, and task B can go to the running state. So all these context switching and scheduling overhead are definitely there in the system, but again, we treat them as negligible for now. Okay, so the worst case execution time is what we saw just now. Then the worst case response time, all right, is factoring in what we call the interference of other tasks. All right. So let's look at this example. So in worst case execution time, this is WCET, we can see that I look at the case where I start the task and I can complete the task without any interference. So when we say interference, basically means preemption. That means some other task comes in to take over the CPU. Right, so that is worst case execution time. That means I run from start to the end without any interruption. But with interruption or with preemption by a higher priority task, this becomes what we call the worst case response time, because now I need to factor in my execution time plus the interference that some other task will preempt me, and then I have to come back in and then complete my task. Right? So the overall response time is now larger. Correct? Because I have to factor in the time that the other task also takes in. So there's another parameter here called the worst case response time. Okay? And of course, yeah, it's possible that task X can interrupt multiple times. Correct? So in reality, a lot of these kind of things can happen. Correct? And for the analysis part, we look at it from with some restrictions, some constraints, so that we can have some idea of what will happen or what will not happen. Okay, but theoretically, yes, a task can get interrupted by another task many instances of time, right? Because if you look at it from the RTX perspective, if I have a higher priority task, correct, that is running. So for example, in the project, if you say that my serial monitor task is higher priority than everything else, and then you keep sending data, all right, then that serial monitor task will definitely be preempting all the other tasks in the system, because you keep on sending data again and again. All right, so it can happen. All right, and of course you need to see whether if that scenario is a valid scenario, whether your serial monitor task should actually be higher priority or should it be in the same priority as the other tasks. All right. So these are decisions that you need to make, okay, while you are developing your architecture. Okay, so in the case of RTX RTOS, like as we mentioned, what we have is a preemptive priority-driven scheduling, where a lower priority task will automatically get context switched off and a higher priority task will take over the moment a higher priority task becomes ready. All right, so that is a preemptive priority driven scheduling algorithm that is implemented in the RTX OS we are using. Okay, so let's look at how it can work here. So I have 3 tasks here, T1, T2, and T3, high, medium, and low priority. So in this case, we have T2 ready at time T equals to 0. All right, so T2 is running. All right, and let's just say that at T1, at time T equals to 15, T1 becomes ready. Okay, so prior to this time, maybe T1 was in the block state. Okay, maybe it was in the block state, maybe it was not even created yet. Okay, maybe in task 2, then you created task 1. Okay, like just now what I was talking about, the OS thread new doesn't have to come in the main. You can call OS thread new later on, okay, while the OS is running. All right, so at T1 you have a new task which is higher priority and is ready. All right, so in a preemptive priority driven system, okay, the scheduler will come in and will cause a preemption, which means that your T1 task will take over. Okay, so when your T1 task takes over, it will run. Okay, and while it is running, if T3 becomes ready at time T equals to 18, okay, T3 is considered a low priority task. So a low priority task, even though it is ready, it is still in the ready queue only. All right, until the higher priority and medium priority are no longer in the ready queue, then the low priority task can get a chance to run. All right, so when T1 finishes, so at this point of time, we assume that T1 goes to either finishes, okay, or goes to a block state. All right, so when T1 goes to a block state, then eventually T2 get a chance to run. All right, so T2, which is the medium priority, will run until it completes, and then only T3 will get a chance to run. All right, so the whole idea is, as you can see, so you can see 2 things. Of course, one thing that is good is the high priority task. Correct? The high priority task definitely gets immediate use of the CPU, which is good, which is what we want. All right, but it also can add another layer of problem because your T3 can end up being pushed further and further down the line. Correct? So it is like being bullied, correct, by the higher priority task. All right, and you may see that, hey, how come my low priority tasks never get a chance to run? Right, because my higher priority tasks are always running. All right, so you need to sort of examine how you assign priorities, all right, and whether the way you assign, because the way you assign priorities can also change the dynamics of the whole system. Okay, in the past, for our project, I believe most students have used equal priority for all the tasks. Okay, and it seemed to work fine. Right, but of course, you are free to change the priorities around and see whether a different approach is better. All right. Again, it all depends on how you write your code, how you design the different tasks to talk to each other, and so on. All right, which we will explore, okay, along the way. Okay, but again, priority itself can have a great impact on the dynamics between the different tasks. Okay, so you have to remember that when you assign priority. Okay, so of course, now comes to this important question: how do we assign priority now? Right, so I have so many tasks, right, and I know it's a priority-driven preemptive scheduling policy. So how do I assign? Right, so you can have fixed priority and you can have a dynamic priority. All right, a fixed priority is one that does not change with time. Dynamic, of course, changes with time. All right, but within fixed priority, you also have this concept of priority dynamically changing just for a short period of time. All right. Okay, so that is what we call to prevent a priority inversion problem. Okay, so in the OS, there could be a situation where you have this priority inversion problem. Okay, we will actually cover this later on. Okay, but in this scenario where you have this priority inversion problem, so what is the priority inversion problem? That means a high priority task actually cannot run because it's waiting for low priority task to do something. Okay, so that is called what you call a priority inversion problem. Right, and of course that is not ideal, correct? Because if you have high priority task, it should run, okay, regardless of the low priority task. Okay, but sometimes because we have shared resources, okay, shared data or so on, then the high priority task ends up waiting for the low priority task to finish something. All right, so that is a priority inversion. All right, so in those kind of situations, we can temporarily switch priority, all right, or change the priority just to fix this problem. Okay, but this is only temporary, and after that it will switch back to its normal setting. All right, so this is actually something that we have in the RTX, all right, which is actually very helpful. Okay, because it can help save a lot of problem, because we did not foresee that this issue can happen. All right, so we will cover that later on. All right, when we are talking about the mutex and semaphore and other concepts. Okay, so let's look at some scheduling algorithms. Okay, so one of the most common ones that has been around for very long is what we call the RMS algorithm, rate monotonic scheduling. All right, and in this rate monotonic scheduling, we have fixed priority assignments for periodic tasks. Okay, and the concept is very simple. Priority is inversely proportional to task period. Okay, and the thinking is simple. If my period is short, that means I need to keep running this task very frequently, then I need to have more frequent access to the CPU, so my priority must be higher. Okay, so that is the sort of rationale behind this policy. All right, so as long as I need more frequent attention of the CPU, my priority should be higher compared to some other tasks that only require the CPU once a while. Okay, so that is the idea behind this. So if I look at this three tasks over here, all right, the C is the computation time, and this P here is the deadline or the period. Okay, so as you can see, if I look at the deadline itself, T2 is the one with the shortest deadline. Okay, so since T2 has the shortest deadline, that has to be assigned the highest priority. Okay, that means T2 will be running first, followed by T1. Okay, because the next one is this. So this is 1, this is priority 2, and this is priority 3. Okay, so based on the period. So T2 will run at the highest priority. Okay, so this is highest priority, this is medium priority, and this is low priority. Okay, so let's look at what happens. So T2 runs first. T2 has a computation time of 1 unit. Okay, computation time of 1 unit. So after it runs, what happens? So since the period is only 4, that means every 4 units of time, then a new instance is released. Alright, so once I compute this 1 unit of time, then I can actually free up the CPU. Right, I can free up the CPU. So the next task, which is in the next priority queue, will be the medium task T1. So the T1 can run. Alright, and T1 takes up 2 units of time. Okay, so this is 1 unit of time, this is 2 units of time. Alright, and once that is done, okay, you can switch over to the task 3. Okay, so task 3 actually has 2 units of computation time. Alright, but you can see that after it completes just 1 unit, the time becomes T equals to 4. Alright, and every 4 units of time, the high priority task will release 1 instance. Alright, which means that I now need to switch back to the task 2. Okay, so at time T equals to 4, task 3 will be preempted and task 2 will run. Okay, and after task 2 runs for 1 unit, then you will give up the CPU, and then task 1 will get a chance to run because task 1 repeats itself every 5 units of time. So just nice, after 4 units plus 1 is 5. So at 5 units of time, a new instance of T1 is released, and T1 takes 2 units of time to complete. And once that is done, we can now switch back to the task tree to complete its computation. All right, so as you can see, there is no issue for task tree because the deadline is here, 20. So from time t equals to 0 to time t equals to 20, I just need to complete 2 units of execution. All right, so that is why you can see that this RMS algorithm sort of works, okay, in most cases, where you can see that if I follow it and I analyze it, you see that everything falls in place quite nicely. Okay, well, of course, it doesn't work all the time. Okay, we will be exploring that later. All right, so here again at time t equals to 8, the next instance comes in, and after that, what happened? 8 to 9. So here, what do you see? From 9 to 10, what happened? 9 to 10, actually nothing happens. That means there is no utilization of the CPU because T2 already finished, correct? And T1's next instance has not been released yet. So the time unit of 9 to 10 is actually a time slot where the CPU is actually free. Alright, so at time equals T equals to 10, the next instance of T1 is released. Alright, it completes, and then again, okay, at 12, T2, alright, and then T15. So here at time T equals T15, the next instance of T1 is released. But before it can complete, another instance of T2 comes in. So again, T2 will preempt T1 to take up 1 unit of time, and then it can go back and finish up. And then it can finish up over here, and then you carry on. All right, so this is basically how you analyze the sort of execution flow, okay, based on this RMS algorithm over here. All right, and what do you see? You see that at 0 to 20, after that, you see that it sort of repeats itself, right? Because the first few starting blocks of this and the first few starting blocks of this looks to be the same, correct? So you can see that the whole sequence, this whole sequence here, will sort of repeat itself again and again. All right, so this is basically what we call the hyper period. Where the hyper period is a period of time where you can actually see that the entire sequence will repeat itself over and over again. Okay, and this hyper period is basically the least common multiple of the task periods. Okay, so when I have 4, 5, and 10, the least common multiple is 20. All right, so the good thing is, if I want to use this RMS algorithm, what I need to do is I just need to simulate this behavior. Simulate, that means like what we did just now, analyze the behavior for one hyper period. And if within that one hyper period there is no deadline being missed, then you know the whole task set is schedulable. That means I can guarantee that if all else remains the same, this entire task set will carry on to be schedulable without any issues. That means all the deadlines can be met. Okay, so that is what this hyper period actually tells us. Okay, so now let's look at some other aspects of this feasible schedule as well as optimal scheduling algorithm. Okay, so I think now mind, what we will do is we will stop here. Okay, so I think another thing that I also want to try to do properly is to stop on time, because I noticed the past few lectures I go all the way for the full 2 hours, and I think it's not fair to those students who also have a class straight after this at 11 o'clock. Okay, so I will try to stop, okay, all lectures by 10:40, 10:45. So you have that 15 minutes break to relax before you go for the next class. Okay, so don't worry about the schedule, okay, whether we are behind schedule or anything. All right, we have more than enough time. Okay, so I planned out everything so that we have more than enough time to cover everything. All right, and even for tutorials, we are going in the correct pace. All right, so there's no point rushing through the tutorials. All right, so we are going at the correct pace to make sure that you understand what is happening. Okay, so there's a question I missed. Okay, what can you explain the priority inversion? Okay, so the priority inversion problem is okay, how do I put it? Okay, so for example, you have a serial monitor, right? So you have a serial monitor and you say this is higher priority, and this serial monitor is supposed to maybe take this data coming in that you're sending through the app, for example, and be able to write to a buffer, correct? And this buffer is being also read by other tasks so that you know what is the command being sent. All right, okay. But let's say you have this this buffer is maybe a file system. All right, so you need to access this file. So you know that in OS, if I open up a file, it's locked. So somebody else should not be able to access the file. All right. So a higher priority task that, let's say, the serial monitor tried to write to this file, but a lower priority task was reading from the file and did not close the file yet. All right, so it is still holding on to this file. All right, but the higher priority task is running and is trying to access this file. All right, and it cannot complete this activity because the lower priority task is holding on to this shared resource. Okay, so releasing the file is something that is the responsibility of the lower priority task. All right, so if the lower priority task has not released the file, then the high priority task cannot get hold of the task, cannot get hold of the file. All right, so the idea is this is what we call resource sharing. All right, so when one task is holding on to a resource, all right, that resource is owned by that task. So regardless of priority, all right, you cannot have, the situation is such that a high priority task cannot just snatch a resource from somebody else. Every task that is holding on to a resource has to take responsibility to use this resource in the right way. That means when I want this resource, I ask for it. When I finish it, I release it. All right, so you come back to this scenario, when my low priority task is in the middle of using this resource, I say using this, accessing this file, and suddenly this higher priority task comes in. All right, so what happens is the lower priority task open up this file, okay, and was trying to read from this file, but before it could finish with this file activity, it got preempted. All right, it got preempted, and then this higher priority task came in. So when this high priority task comes in, what it tried to do, it tried to access this same shared resource, which is the file. But then it cannot access it because it is still in the midst of being used by low priority tasks. All right, and because of this, we say that a priority inversion is happening because the high priority task is now waiting for low priority task to finish. Okay, so yes, it is what we are saying is blocked. All right, so what will happen is the high priority task now has to go to a, in a sense, a block state, because the high priority task is run, but then it cannot do what it's supposed to do. Okay, so when the lower priority task gets preempted, so because a lower priority task does not know, or not any task does not know when it's going to get preempted. Right, that's the nature of OS. Right, so it could have been in the middle of anything. Right, so it could have been writing to a file, it could have been sending data, it could have been processing some data. So at any point of time, it could have been preempted. So there's no way for a task to say that, oh, I'm going to get preempted, I must quickly finish this. No. Whatever it was doing, it can suddenly just get preempted. All right. So when that happens, so when the preemption happens, yeah, it just suspends whatever it was doing, and the OS switches over to this higher priority task. So when the higher priority task comes in, and then it realizes that I want something that the low priority task is actually holding on to, then I cannot do what I want to do. All right, so then this priority inversion thing happens. All right. Okay, so this dynamic priority thing, solving it, we will cover in the next 1 or 2 slides later. All right, so I want to go in the proper sequence so you understand the sort of application aspect of this. All right, so this ties to the mutex and the semaphore and this how we handle resources. All right, so we will actually come to this later on how we are able to solve this. Actually, we don't need to solve it. The OS actually solves it for us in the background. All right, okay, by sort of implementing this temporary change in priorities. All right, so be patient. We will come to that in I think the next 1 or 2 slides. Okay, so I will end here. All right. Again, thank you for coming in today. Those who have questions can stay back and ask. Okay, if not, I will see you all. Okay, so as I mentioned, Friday this week onwards, Fridays I'll also be there in the lab. All right, because I think it's been quite tiring for the TAs to handle both the online students as well as the physical students concurrently. So I'm also going to be there. All right, so any questions, okay, for the lab and what you're trying to do, we can also discuss during the Friday session. Okay, you can have multiple threads for the same function, yes. All right, I mean, it's just like writing a function is just a piece of code that can get called. All right, and multiple threads can call the same function. All right, of course, there are also certain rules to follow, which we'll also cover. Okay, on functions that are shared across multiple threads. Okay, so there are certain rules you must also follow to make sure that things work correctly. Okay, so that's all I have. Thank you very much. All right, so I will see you all on Friday, those who are coming to the lab. All right, so as much as possible, try to prepare a bit, okay, on your own, so that when you come, I mean, actually the lab you can do it on your own time. All right, so when you come to the lab, you can focus on fixing up the hardware, all right, and testing and drivers and all this other stuff. All right. Of course, any questions you have, you can also ask me in the lab. Okay, so for the delay, okay, so if I were to use, okay, so this is the timeline just now I showed you, all right. For the, okay, so if I were to sort of look at it from the normal delay perspective, what will happen? So if let's say this was replaced with a normal delay, then what will happen? I will still be in the run state only, all right? I will never transition to the block state, all right? So what will happen is, after 5 ticks, yeah, after 5 ticks, what will happen is I will transition over and then I will run. So I do not know when this 5 tick would happen, all right, exactly based on this code itself, but after 5 ticks, I know I will transition over and I will run. All right, but in the green thread, you go to the block state. All right, so since I go to the block state, I will come back here and I will carry on to be in the run state. All right, of course, when I say run means you still go to the ready state and then run. Okay, so when you get transition out, okay, due to the timeout, this task will go to the ready state. Okay, and this task will run. Again, this task will run until it gets 5 ticks or the block. When the block is executed, then you can switch back to the LED red thread. So the only difference is your LED red thread will forever be only run and ready. It will not go to a block state. Whereas the green LED thread will transition between run, ready, run, and blocked because of the OS delay. So that is the difference in the timeline between this implementation and the OS delay implementation. Okay, the round robin effect will happen as long as you have more than one thread in the ready queue and these threads are having the same priority. Doesn't matter how long they have to run. Okay, as long as they need to run, that means they are both in the ready state, right, and they are both in the same priority level, then this round robin effect will kick in. Okay, so basically you should not use a delay anymore, all right, in your code as much as possible. You should use OS delay as much as you can. All right, the delay is something that we used in the first half because we were still in a single-threaded environment, right? So now that we're switching over to a multi-threaded, we should use OS delay again as much as possible because that is a more effective use of the CPU's resources. Round robin, yes, each of them take turns to go around. Okay, that means all the tasks that in the same priority, each will have a same amount of time slice. Okay, whether we want this behavior or not is something that we can actually control, okay, which we're actually doing in this week's lab. All right, but the default behavior is that this behavior is enabled or this feature is enabled, and the rationale for that is the thinking that if I have different tasks which are in the same priority level, then they should all have an equal share of the CPU. All right, because if we say that higher priority takes over a lower priority, that is fine, but within the same priority, the thinking is they should have an equal share of the CPU since they are already designated as equal priority. All right, so all of them have a same share of the CPU, which in a sense makes sense because since you already said they are same priority, they should have a equal share of the CPU while there is no other higher priority task that wants to use the CPU. Okay, so it's already 11, so I think I'll end here. Okay, so thank you very much. I will see you all on Friday, those who are coming. Okay.